Although this won't come up very frequently in this course, we should investigate how a radial velocity profile affects flow through a pipe. So what do I mean by that? Well, let's say that we're given a system with steady water flow through a pipe and that the water has constant density, meaning it's uniform density everywhere. Now that should be true for water. Water is incompressible. But it has a radial velocity profile, by which I mean that the velocity is different at different radii from the center of the pipe. So the form I've picked is that the velocity as a function of r is some constant v0 times the quantity 1 minus r over r pipe, where little r is measured from the center of the pipe. So little r equals 0 is the middle of the pipe, little r equals big R pipe is the outside of the pipe. And if you graphed it out, it would be a straight line, right? So the left-hand side of the graph represents the interior, the center of the pipe. So if you're at the exact middle, then you have the maximum speed. If you're at the edge of the pipe, that's the right-hand side of the graph, that means that you're down formally to zero velocity. If you prefer to visualize velocity vectors for the flow, then the pipe would look something like this, where the largest speed, the longest vector, would be in the middle of the pipe, and then near the edges it would get smaller and smaller. That's all we're talking about. Now this is not necessarily the most realistic flow profile, but it's one that we can integrate. That's nice. Okay, so the expression for m dot through this pipe is the integral over area of rho times v, where v has ears, so it must be velocity in this context. So we can pull out rho. We said the density is constant. Now we just have the integral over area of a velocity. This is the part that I want you to see, because if you haven't done an integral like this before, it's not trivial. So first we can substitute in the expression that we have for the velocity. That's not too tough. And we have all of this. Now we have to decide what to do with that dA, because the only variable we have in this expression is little r, but we're trying to integrate over an area. Fundamentally, this has something to do with polar coordinates, and you may have seen this before if you've taken classical mechanics or electricity and magnetism, but we can pull a trick with that differential. We can rewrite dA as the product of r dr d theta. If you don't believe me, I'll sketch it out here. You may need to encounter this more formally in a math course, but let's say that we have a circle, so this could be the cross-sectional area of our pipe, and we're interested in a differential area element, which would be just a little piece of this circle. Well, actually, if we're going out radially, remember the radial direction is out from the center, then one side of that little section is dr. But what to do about one of the other adjacent sides of that shaded region? Well, let's think about what a differential angle would look like. So if we measure this in terms of angle, little tiny angle, then d theta is what I've just shaded in white. That's d theta. But you can't just multiply d theta by dr to get dA. It has the wrong units, for one thing. dA has to be a differential area. R has units of length, but theta does not. Theta is an angle. So it turns out that the other side would be r d theta. That's the radial position of that little gray region times now the differential angle. That correctly gives you the length of that side, and if you want to get an area, then you multiply dr times r times d theta. That's where you get the expression that dA equals r dr d theta. You can use this without understanding it, but isn't it better if you can draw that simple picture and convince yourself how it must work? So now we can substitute that into our integral, and we can separate out the area integral into a part that's over theta and a part over r. We have the same integrand, but now the differential has become r dr d theta. So let's separate out the theta integral and the r integral, which we can do because, remember, the velocity profile only depends upon r. So one of those two integrals is very easy. It's the integral from 0 to 2 pi of d theta. That's just going around the whole circle. That'll turn out to be 2 pi, so we'll pull that out front. And now we just have a relatively straightforward integral of the quantity r minus r squared over r pipe dr. I just pulled that r from the differential into the expression in parentheses. So let's move that up. And now we can just separate that integral into two pretty simple integrals. So we keep the constant out front. We have the integral of r dr minus 1 over r pipe, the integral of r squared dr, both integrals going from the center, namely r equals 0, to the outside of the pipe, r equals r pipe. Okay, so we can solve integrals. The first one's just going to be r squared over 2. The second one's going to be r cubed over 3 with that 1 over r pipe out front. So we'll simplify things a little bit, and we have two factors of r pipe squared that we can pull out. That just becomes 1/6 in the brackets, and so the full expression for m dot is pi rho v naught r pipe squared over 3. So this is the case with radial variation. That's the m dot that we calculate. Now this probably doesn't mean much. But what we could do is compare to a different case in which we had no radial velocity profile, namely that the radial velocity was constant and uniform throughout the pipe. So let's do that now. We'll keep this result up there. What would have happened if the velocity had just been constant and uniform everywhere? Well, for that case, let's consider what I call m dot c. The c is just for constant velocity. So that's equal to, again, the integral of rho v times dA, except now both rho and v naught are constant, so we can pull them both out of the integral. The integral of dA is just the area of a circle. It's pi r squared. So m dot c becomes pi r pipe squared rho v naught. We can take the ratio of m dot v to m dot c, and we see that actually most of the stuff matches up. Pi r squared v naught rho, that all cancels, and we're just left with that factor of 1/3. So m dot v over m dot c equals 1/3. What does this tell you? Well, it tells you if you had assumed, for the case with a radial velocity profile that we had specified over on the left, that the entire flow was a uniform velocity at the maximum flow speed, then actually you would have overestimated your flow rate by a factor of 3. So you would have gotten the wrong amount of stuff through your pipe, and that's simply because the flow is being slowed down as you approach the edges of the pipe. As I said before, this may not be the most realistic velocity profile, but you can imagine in any real pipe, you'll get a different result if you have variation within the velocity, and the only way to treat that properly is to do this integral. Generally in this course, we're going to try to overlook that detail, because it would be a pain if every single open system problem you had to deal with, you had to do an integral just to figure out what was going through the pipe, never mind all the thermodynamic stuff we have to do. But it is good to see this once, just to see how much the velocity profile can change your flow.